Hi, and welcome back to the AITX Community Podcast, the show where we go deep with some of the most interesting AI engineers, entrepreneurs, researchers, and operators across the state of Texas. I'm your host, Jake O'Shea. Our mission with this podcast is to pull back the curtain on what's really happening in AI in a way that's accessible and engaging for anyone that's excited about the future of this technology. We specifically focus on Texas because we believe that the Texas engineering community is seriously underrated. People here are building incredible products and solving difficult technical challenges, and our hope is that this podcast helps expose some of that exciting work to the rest of the world. This week's episode features Ashia Lewis-Livaudais, a physicist, frontier AI researcher, and the founder and CEO of Symby AI. Our conversation spans Ashia's personal story growing up in New Orleans and eventually getting her PhD in computational physics, through her professional experience as a self-described research engineer, as well as how she got started building AI models to help advance science, which eventually led to her founding a startup, Symby AI. Symby uses advanced AI models to help researchers do better science. Their platform automates peer review and experimental replication, helping make sure that the science that is done is valid and can be replicated by other researchers. Unreplicable science is a huge problem, which has led to decades of wasted effort by scientists and millions of dollars in wasted research funding. Symby's tackling this problem head on and has the vision of becoming a core feature in how science and research are done in the future. Ashia is one of my favorite engineers and entrepreneurs that I've had the pleasure to work with. And what she's building with Symby is a great example of the types of incredible companies being built right here in the Lone Star State. I think you'll really enjoy hearing her story. Now, without further ado, please enjoy this deep dive with Ashia Lewis-Livaudais.
It's official.
We're live. Ashia Lewis-Livaudais, thank you so much for joining us today on the AITX podcast.
Yes.
So want to get started by giving listeners some context on who you are and kind of where you came from and really what first got you interested in research and technology. And so to start, like we both have a common connection to the city of New Orleans and just the state of Louisiana.
Indeed.
You grew up there. My family came from there. To start, like tell us a little bit about kind of your life growing up and what initially kind of spurred your interest in science and technology.
Yes. So hello, everyone. To piggyback off my introduction, I'm Ashia Lewis-Livaudais. From New Orleans. Also lived a little bit in Texas on the later end of my developmental years. But so when I was younger, I thought I was going to be an entomologist. To this day, I still have an obsession with bugs. I probably will be an entomologist in my later years. I've got a great photo album of the best bugs in Austin that one would see. But that was really what sparked it. I would find all different types of bugs or arachnids that I was interested in. And as one does, when you are a child with very little barriers on what you think you can do, I would create little obstacle courses for said bugs.
Nice.
That really got me interested in like basic mechanics. And so when I was growing up, one thing that my guardians at the time were really good at were making sure that little books that just so happened to coincide with my interests were lying around when I had a question. And so I really got interested in like very low level baby's first mechanical engineering stuff when I was younger, to build these obstacle courses, torture devices sometimes. Obstacle courses for bugs. So, but long story short, that got me into it. Going deeper into the engineering though, at some point when I was really young, I discovered like as one does when you're an angsty young person, the Mouse Utopia experiments. Just for context for everyone, there were these early experiments where guy tries to create a mouse utopia. So it's this huge structure where he has a bunch of these mice, and they are living their day-to-day with ample food, ample water, ample play space, and it was terrible. What ended up happening was essentially the breakdown of a mini rodent society, where essentially the takeaway was that even if you provide ample resources, living in this constrained environment wasn't good for those organisms. And so, again, as one angsty person does, you think about that and you're like, I wonder if you could do that, but right. In a way where you don't terrorize thousands and thousands of mice and kill them. And so anyway, that got me interested in maybe not necessarily the social sciences, but in neurophysiology, thinking about the biomechanics of what it means to be a human, of what it means to be an animal. And from there, I then discovered artificial intelligence, which back in the day at that time was early deep learning in that neural networks are a thing, but the frameworks and engineering around them are super rudimentary. And so, yeah, that's kind of what happened with that. So.
Okay, so bugs kind of spurred everything.
Yes, bugs,
what were
rats,
some of the
critters.
bugs in New Orleans? Like, what were some of the common types of bugs?
Oh my God, my favorite bug. So best bugs in New Orleans, like by and large, family-wise, would be any sort of beetle that you find in New Orleans. New Orleans has really, really great, juicy, big. This is, of course, the content that people are coming for.
I love it.
In this podcast. Green beetles. Obviously, when it comes to any of our similar to bugs, arthropod friends, New Orleans is kind of known for that. But great bugs, great spiders. The arachnids there are amazing, incredible. Shout out to the brown recluse. Shout out to being bitten 3 times. So I think I'm immune now. Whatever, that's cool.
Those are the poisonous ones, right?
They are venomous, yes, but different people have different reactions. Like some people, you lose a leg, and some people, you might lose like a little piece of skin. Like myself, like I definitely experienced necrosis, but it's just very minimal. So.
Wow. Okay.
Indeed.
All right. So critters kind of spurred you to this interest in like mechanical physiology and science as well, right? Like
yeah,
the
pretty much.
Utopia experiment. So where did that lead you kind of when you graduated high school?
Yeah. So by the time high school came around, I was really deep into, I have to study physics. Mm-hmm. For me, physics was so, yes, I was interested in building things and even understanding the human as a machine that just has very intricate componentry, right, that one can understand. But like I said, by the time high school rolled around, I was really like deep into, I had to study physics because it's essentially the study of how to break the world apart and build it again or build other worlds, which I thought was exceptional and phenomenal as somebody that like enjoys philosophically just like feeling like I'm studying like limit breaking things. And so it seemed like a no-brainer that like physics was kind of the way to go if you want to understand the world at this really fundamental level. And so for me, that's where I was in high school. Coming out of high school, I also knew at the time that I wanted to do some sort of computational physics when I got into school, because although it seemed like we had all of this interesting theoretical foundation for physics at large, in all of its subfields, the computational aspect of what it takes to actually do physics, validate physics, not even just physics, but that was my focus at the time, was incredibly behind. And so for me, it seemed like there was a computational bottleneck. So much so that like I had a teacher, bless his heart, that was a physicist that just liked teaching, that said, don't do physics. You're not going to do anything that's going to be worthwhile if your worthwhile is, again, a foundational understanding of the world, which was incredible for me to hear because it was completely antithetical to my thinking. And so I'm like, okay, what's the bottleneck there that he might be addressing? I thought it was computation. My bet's still on some computational limits on what we can actually study. So yeah, that was my goal at the time. Yeah.
Okay, so you study computational physics in undergrad. You then go get your PhD. Right?
Yes, correct. Uh-huh. Yeah, so in undergrad, I just studied physics, right? I was physics, bio, and CS.
Okay.
Going into trying to get the foundations of what it might take to study computational physics. At the time, I also, given my background as like a Frankenstein creator of monsters, I was like, yeah, biophysics makes perfect sense for me with this computational bit. But I ended up doing basically more like particle, even physical cosmology, environmental physics even before like straight up biophysics. So yeah, but I undergrad physics, grad school, studied computational physics. For context, right, a lot of people don't necessarily even know what that means. It sounds like a fake and phony science, understandable. But it really is just supposed to be the bridge between the theory and the experimental, right? So it's very math heavy, very CS heavy, but asking about like what is computational physics to physics is like asking what is linear algebra to machine learning, or what is linear algebra to AI. You don't really have a lot of the ability to move forward on discovery without that base of computational physics. Because a lot of the systems that are interesting for us to study you can't solve them mathematically by hand. You can't solve much about them mathematically by hand. So that's where computational physics comes in.
Yeah, well, and especially when you think about how far physics has progressed, it's like way beyond measuring how fast apples fall from trees.
Unfortunately.
And then using that to figure out gravity, right?
Yes.
We're now in like quantum physics and quarks and all these other things that
absolutely
require kind of some sort of computation to measure.
Yeah, absolutely. Like even computational physics could even be, and we'll probably get into it more later, like we were looking at particle accelerator optimization. That's a form of computational physics, even looking at the hardware and saying, how can we optimize this stuff so we're not spending millions of dollars every time we want to make a like low-level discovery that people are going to forget in a year. So, yeah.
Okay, so you go to school, you get your PhD in computational physics.
Yeah.
There's a fun story that you told me about your time living on a reindeer farm in Russia.
Indeed, yeah.
Tell me a little bit about, tell me that story again.
Yes, so I am a Slavophile. Probably anybody that knows me knows that I am a Slavophile. I love Russian language, love Russian culture, love Russian literature. It's been like my Russian literature is basically my love language. If you want to really spark passion in me, quote something at me from one of my favorite Russian authors. You'll get me easily. So with that being said, we actually had a program during it's kind of the back end of my undergrad years where essentially they would ship you off to somewhere in Eastern Europe for the equivalent of like a student exchange program. And so for me, I was like, hell yeah, I'm going to Russia. Like I know the language. I finally get to go in real life, in real time. That'll be cool. I want to eat all the borscht. I'm going to have a great time. So I stay with the fantastic host family firstly, and I am there, and I just think one day, oh, I'm like 1 month over the time that I'm actually supposed to be here. I'm supposed to be back in the United States. And so it just so happens that I guess my university just kind of, shout out to them, just forgot.
Let's name them.
University of Alabama.
Roll Tide.
Roll Tide indeed. We're gonna, right, name and shame, exactly.
Yeah.
Name it or keep it on the playground, you're right. But anyway, Roll Tide, they forgot me.
So you were living on this reindeer farm with your host family, studying
I wasn't
math.
even there yet. I was
okay.
This was like Central City, Petersburg.
Okay.
Right. I wasn't there. I was very much in the city, where everybody else is, in the middle of it. Then I decided, well, I'm here. School is out. Even the exchange program is out, right? I'm just gonna travel. I did this in Alabama too. One of my things that I like to do to relax is just to like visit remote locations. Now, given only Jake sees what I'm doing, that's a little shaky depending on where I am, especially sometimes in the South. But I figured, why not do something similar in Russia? And so it's very easy to visit some of the remote locations that are sort of southern. Where it starts to get challenging physically is when you move up north.
Siberia.
Exactly,
yeah.
Because you move closer to that pole of cold, as they call it. And so that's obviously where I wanted to visit. And so that's really where the reindeer herders, really, I call them farmers, but reindeer herders are. There's some in Yakutia, but there's some other smaller and similar villages and groups of people out there. I stayed in a structure that's the equivalent of a tent for quite a while. They put my ass to work.
Herding reindeer?
No, I didn't even get to do the cool stuff. Oh. I was mostly just doing like some forms of chopping and or storage and or preparing food with insert babushka here. I wasn't even doing any of like the real cool stuff. But I did leave with some very interesting garb. Like I still have a very nice coat, very nice shoes, made completely from insert different parts of reindeer, which is really, really fascinating. But what I love about them is that they are such an optimistic people. There is this like Russian identity at large where even if you have completely divergent identities, there's still this like undergird of, I call it cynical optimism. I find that surprisingly, that was kind of the same for the herders out there as well, despite them being so cut off from the city center, right? They were incredibly optimistic, incredibly sweet. I didn't stay I stayed with one group for quite a while, but even if I'd moved, and I did towards the end of my travel there, it was very easy to not only make friends, but make what seemed like family.
Yeah.
They were just very accepting. I've never experienced something like that before where I felt so like I felt very human. It was interesting. So
Something about like tough conditions that I don't know.
yeah,
People,
maybe that was it.
they have to deal with so much just for like day-to-day life that I feel like it makes them a lot more, friendly and accepting and just like
For sure.
appreciative of human company.
Oh, for sure. Yeah, that's definitely a good point. Well, I sapped up all of their company, and they definitely sapped up mine. But like I said, they were definitely putting my ass to work too. I think they were just happy to have like, oh, a laborer. Sure.
Awesome.
So that was really interesting. But yeah, visit remote place. Well, let me not actually put that out there. I don't know. Visit remote places at your own peril. I should say.
Fair enough.
Yeah.
Fair enough. So you come back to the U.S., you finish
Yes.
your PhD. Tell me a little bit about the research that you were doing while you were there. You mentioned, I think, particle accelerator optimization.
Yeah. So I actually took quite a while to sort of find my identity with physics, right? I'll jump forward a little bit and then jump back. What I am at my core is a research engineer. And that title for a researcher is still very nascent, right? There is, despite the, really old relationship between research and engineering, having an identity, or at least an occupational identity that is very much both of those, having prowess in each, is a newer idea, right? You've always had researchers that have done some kind of programming, but they're not necessarily good at it because they don't want to be good at it, right? They have other things that they want to do. But now that, especially with AI, but especially as computational becomes an even grander part of how we think about science is at a core, I think we'll see more research engineers specifically. I say that to say, again, I took a long time to sort of find my identity in physics, right? I did computational physics when I was in school. That's what my PhD is for. Great. Like I said, that was mostly aimed at physical cosmology. But when it came to actually working in the lab, first place that I worked was at the Smithsonian, their environmental research center, on this very long-standing, damn near a century-old project. It'll also end by the time, when we die, it'll still be going. When the next generation dies, it'll still be going. It's one of the Smithsonian's actually earliest research projects altogether. But it's called Biodiversity. It's environmental physics. That's environmental physics experiment that is studying different macro and micro effects of climate change at large. And so they've got this huge plot of land with these sensors where they're collecting trillions and trillions of data points per week on, like I said, macro and micro metrics that are associated with climate change.
Temperature, humidity, precipitation.
Exactly, yeah. They also look at things that impact some of the microbiomes or larger biomes that exist in the region, right? So they can say, hey, over this longitudinal period, if you have this macro or micro change in a biome, this is what you can expect to happen to the bacteria in that area, or the deer in that area. Really, really cool stuff. My job when I went there was, one, to think about how to actually sort of modernize the research that they were doing, but also how to modernize their technological infrastructure. So I just told you that they were taking in trillions of data points of sensor data per week. This was by hand.
Holy cow.
At the Smithsonian. At the time that I was there, the Smithsonian had 2 data engineers. Not the Smithsonian Environmental Research Center, not this lab that I was in, the Smithsonian, as an institution, had 2 data engineers working, which is fantastic. So basically what I did was jump around these labs and, again, try to say, okay, how do we create actually a core technological infrastructure that y'all can use for this big-ass project, but also that I can port for people in this lab, in this lab, in this lab. That was incredibly fun work. I loved doing the research aspect, but I found that thinking about how to actually translate their needs into the tech, whether I'm introducing them to deep learning or statistical methods that might be useful, or setting them up in a cloud environment, right, doing like VM deployments for them, was super cool. And so I did that. I then, moved on to Fermilab. Again, one thing that's also important to mention, I've always worked as some form of engineer, just pure engineer as well, on top of being an academic, because being an academic does not pay. So that also...
Tell us a little bit about Mercury Data Science, because that's where you spend some intermediary time, right?
Yes. Yeah, so that was really... How do I put it? What that helped me understand about myself is that when it comes to your usual engineering environment, I am unemployable. I will go ahead and say that. It also helped me, again, harden that identity as I need to be a research engineer, because it was the first time that I ever felt like I was actually stuck in an environment where I had to do something that I didn't like at all.
Just the pure engineering.
Just
work.
pure engineering. Yeah. And it was a biotech, or health bio startup, basically the bio or engineering consultancy for different people in bio and health. It should have been interesting on its face, but for me, it simply wasn't. I was stuck on projects that I didn't give a damn about. I was doing engineering that I didn't really care about. I was following by the book procedures that I didn't think were the best for what we were building, but it wasn't my place to say. I was taking off projects that I did find a little bit interesting. So that really helped me understand that, hey, although I've been doing this kind of stuff in the background to kind of like pay the bills, I love suffering at the end of the day. I'm a big masochist. Like, I can just go and be the research engineer and take a little pay cut. So.
It's that Russian literature really stuck with you.
Indeed, yes. It's the cynical optimism in Reindeer herding. It really gets into the bones. But great job, great people. Also really inspired how the kind of environment that I try to create at Symby when it comes to the actual company. So let me not just say that it was a terrible experience. It wasn't. But it just also, like I said, helped me build a philosophy on how what I like to work on. And so, yeah.
Well, I think it's really interesting, like those two archetypes of a researcher versus an engineer in many ways are very different, right?
Indeed, yeah.
Engineers their job is to take this thing that researchers have validated is real and works and actually start implementing it in the real world, optimizing it, miniaturizing it, XYZ, right?
Exactly.
Whereas researchers are very much, okay, here's what we know so far, here's the studies or the science or the hypotheses that we want to test to validate what's new.
Exactly.
Right? And for you, it's kind of that intersection of both, where you want to be kind of on the cutting edge, seeing what's new, but you also want to be part of actually implementing it, making it scalable, making it replicable, things like that.
Exactly, yeah. I would personally feel like a worse researcher if I was a bad engineer. And I would feel like a bad engineer for what I do if I was a worse researcher. Yeah. So for me, the two are important to bolster each other. Like, I can't really be a good one without the other. So
from Mercury, you then moved to Fermilab.
Yes.
I think for folks that aren't familiar, like, what is Fermilab?
Yes. So Fermilab is a particle accelerator research institution. People are probably more familiar with CERN or the Large Hadron Collider, which is actually the same thing, plus some other cool stuff with physics.
And Large Hadron Colliders, correct me if I'm wrong, it's a giant underground tube where you start accelerating particles as fast as possible to make them collide together.
Perfect.
And that creates all sorts of new, interesting results, basically.
Exactly. That is exactly right. And so Fermilab is essentially the U.S.'s answer to the particle accelerator.
Okay.
So we have the less cool Tevatron. Well, it's cool.
It's pretty cool.
But like I said, CERN and the LHC, Large Hadron Collider, tend to get the glory because it's huge, it's big, it's the biggest.
Yeah.
The biggest and the best. And so, but Fermilab also does a bunch of other cool physics-related work, right? Like, it's not all particle accelerator. You have cosmologists that work there. You have people that are straight up astro when they work on galaxy morphology. I worked with some of those folks. You have biologists, actually, that work at Fermilab. It's on a bison plot.
Also in Alabama, right?
Fermi? No, Fermi's actually in Illinois.
Oh, okay.
It is in Batavia, Illinois,
okay,
which used to be a village. The Fermi directors of the time bought the village from the people that were living there and kind of displaced them, but left the homes. And now if you're a grad student working there, you can live in the village while you work at Fermi. So, but yeah, it's in Illinois.
Got it.
Yeah.
So you're working at Fermilab. What kind of stuff were you doing there? It sounds like research engineering work, right?
I was doing a lot of research engineering work. So much like I did for CERC, the Environmental Research Center for the Smithsonian while I was there, a large part of my work at Fermi too was also like setting a technological basis or standard for how we were going to do code and software at the lab, at least in relation to those who are working in like cosmology and particle stuff. And so this was stuff like literally, how do you set up a repo appropriately? How do you package something? What's the best way for us to containerize research so that we can have people automatically replicate it? We'll get to that later too.
Oh, for sure, yeah.
So we weren't running into the issues that we were running into when we were trying to validate papers. But also like, what is a better way for us to build libraries or packages on top of the high performance computing stuff that we did? Because like that stuff is hard. It's not particularly easy, and as a researcher, you don't want to spend your time fiddling with how to do HPC stuff.
Yeah.
And so I did that. I worked with cosmologists and astrophysicists to do like galaxy morphology classification. So creating these really strong algorithms to classify different types of galaxies based on very, very, very low resolution data. But one of the really cool things that I worked on that I talk about all the time that also catalyzed my desire to build Symby based on looking at the literature in this field was particle accelerator optimization. And so that's essentially using deep learning, so AI, to optimize how particle accelerators run. They are very expensive and very lossy, which means that we spend a lot of money, millions of dollars, in order to maybe get results that are useful and also maybe get results that we can understand that aren't too noisy. Essentially, our study was, how do we make this less noisy, substantially less expensive, and just costly to operate? And so we did a lot of good work in actually making that happen. So yeah, it's cool stuff.
And so while you were there, there were a lot of really interesting advancements with transformer architectures and language models, right?
Yeah.
So tell us a little bit about kind of the early inklings that eventually led to Symby, which we'll dive deep into later.
For sure. So an interest of mine that started to rear its head very early on when I was at the lab, so we would have an internal journal club, and somebody that I looked up to there and still look up to this day was starting to get into quantitative epistemology for basically mining information from physics papers.
Okay, so first,
yes.
Who is that person? Because it's always...
Oh, yes, Brian Nord.
Shout out Brian.
Shout out Brian, fantastic physicist, lovely man.
Nice. And then define in kind of very accessible language what quantitative epistemology is.
Yes, so quantitative epistemology is essentially, in relation to science, is trying to build out a very tangible approach into how we understand knowledge. And what I mean by that is, when I say knowledge, oftentimes you're thinking about, a very high level philosophical abstract thing, but can we actually define knowledge as like a tangible packet of information? And if we can we also define how knowledge moves or operates? So for instance, right, if I'm saying, if I'm building a system, right, and I'm saying that I want to study the evolution of the transformer, right? The evolution of how LLMs operate over time. Can I define what I'm actually saying when I say transformer? And can I also make real-time systems that can look through literature and show me kind of a step-by-step transformation of or evolution of the transformer or the LLM?
So like quantitatively process
how do we
idea of the knowledge of transformer.
Exactly, yeah. How do we build quantitative systems for understanding like how information works?
Okay. Sorry. Took you off track a little bit.
No, you're good, you're good.
Brian Nord, shout out Brian.
Yes.
Starts talking about quantitative epistemology.
Yes, for sure. Starts talking about quantitative epistemology. I'm all on board. My little pet project at the time, or pet interest at that time, that I started going to a bunch of conferences for, was on meta-learning. And so meta-learning is essentially this really cool idea of, before the popularity of maybe transformers and LLMs, how do we actually focus on teaching deep learning systems how to learn? A lot of deep learning research generally, and still today, is focused on, okay, can we apply existing architectures to this new application? That's great work, but there is a sort of meta-learning layer there where if we can teach these systems how to learn more efficiently, we can do incredible things with incredibly less compute resources, which should always be the goal. And so from getting into meta-learning, I then... transformers were all the rave at the time. there were a ton of people trying to apply meta learning techniques to the transformer architecture.
And really quick, just so this makes me think of kind of this idea of a black box, right? Where you've got these AI models where you put input here, you get some sort of output that you're looking for here.
Yeah.
But the process of how it transforms that is kind of this black box. Like you don't know exactly how it works.
Exactly.
Is meta learning basically trying to understand how the black box works?
Kind of.
Okay.
Meta learning is trying to do two different things, right? And there are two subfields of meta learning that we could talk about too here. Meta learning is not only trying to understand how the black box works, but also optimize said box once we understand what's actually going on. So yeah, we got to know what's going on first, and that's called mechanistic interpretability. And so that is really understanding the mechanics of what's actually happening, that black box. Where meta learning comes in is, okay, once I understand the mechanics, how do I then create algorithms on top of that to constantly have that be optimizing on its own time without the human having to be continuously putting in input? Does that make sense?
Yeah, it's kind of like a perfect example also of this idea of research engineer, right? Because you've got the research of like, how does it work? What's the mechanistic interpretability of the system? And then the engineering work of once you understand that, how do you optimize it, build on top of it?
Exactly. And then that is exactly why I said earlier, I think the research engineer title specifically is important for people to embrace now, because I do think that we're at a point, especially with stuff like this, where in order to be a good researcher, you have to be a good engineer.
Yeah.
I think we're there already. I think we've been there for a while, but
Definitely
we're especially there
AI.
now.
Yeah.
For sure within AI. But I think we're still a little bit behind on getting people to be good research engineers, which I guess is something that we can get into as well. But yeah, that's back to the how do we get started? But yeah, so a lot of people applying meta learning to the transformers. My sort of, okay, how do we see if this is actually working, was doing this really mini project where I wanted to build a knowledge graph for physics papers, right? There had been some kind of fuddy-duddy knowledge graph solutions of papers going around here and there, but I wanted to build something that was actually able to dig into the context and be a little bit more aware about what was actually happening in the paper. A lot of knowledge graph papers or knowledge graph stuff earlier on was like authors related to this author's related to this institution, and that's cool. But what I really wanted to see was, could I create a map of different sub-concepts in physics with
so
these
not just like
transformers?
who's writing it, when are they writing it,
Exactly.
how do they work with each other, but actually like the contents of the paper and relating those things to each other.
Yeah. So if people in the audience are familiar with like forking, right? Forking a repo, right? So you have one repository of code, you create a fork on it, and you make little changes here and there. Research actually operates quite similarly, where a lot of the advances that we make are iterative forks of previous research. What I wanted to do was build a map of those forks for physics at large. And so early LLMs seemed like a perfect step up from like a BERT, for instance. Early large language models seemed like a perfect step up for BERT to help me actually do the processing work to make that map. It was hard. They were not. At the time, they were still a little bit too rudimentary, even with all the bells and whistles. But a lot changed over like the year when I first tried to do that, which was like 2019, 2020 maybe.
Okay.
Yeah.
So you go out with this goal of kind of creating a knowledge graph of like essentially the epistemology or like the process of building on top of things of physics, right?
Exactly.
So how'd you go about doing that?
Yeah, so the way that I went about doing it was batch ingesting, quite similar to what I'm doing for Symby, batch ingesting all of the open access papers related to physics that I could without breaking my bank. So just archive.
For sure.
Just archive and APS open access. I did do that too. Batch ingesting them, then I built this pipeline at the time using BERT, and then I graduated to GPT-2. Then to GPT-3, and as they came out, tried to do more and more. That essentially would have them build these JSONs, so these JSON files that tried to get the major conclusions, methods, and sort of novelties and insights from papers. And then what I had that do is I started with a sample set of about 100 from the two sources that I told you about. And then what I had it do was actually try to see if I could get the LLM to operate almost as a graph orchestrator for me. Okay. And so I actually tried to have it build links on those 100 papers and see how well it did. And honestly, it didn't do the greatest with pulling out different types of conclusions from the papers. But even then, there was a lot of promise with LLMs in relation to creating sort of or working with graphical information, because it actually did really well with linking stuff.
Well, let's talk a little bit for folks that might not be familiar.
Yeah.
What is a knowledge graph and how is it different than a language model?
Oh, yes. So a knowledge graph is really a data structure that takes different, or that takes the same type of information and just shows if they're linked. So for instance, right, if I'm saying I have a knowledge graph of social media, for instance, a social media knowledge graph, what that'll probably look like is that you have a user is one type of object in that graph, and then on that user, I want to see what other users they're linked to. And so those links are called relationships, and those relationships just describe how two users are linked. So for instance, if I'm following Jake on YouTube, we are two nodes that are linked by a following relationship where I am following him. Mm-hmm. However, if we are friends on YouTube, I don't think YouTube actually has a friends option, but imagine it did. If we're friends on YouTube, that's a different relationship, but we're still linked. And so a knowledge graph is essentially a data structure that allows you to define all of these linkages for objects for a system at large. And so for what that looks like for scientific papers is scientific papers generally have people that write them, so authors. They generally have places where those authors work, so like a university or a laboratory, and they generally have content in the paper. That content is usually how they wrote the paper, right? How they actually did the work or the experiment, and what they found. And so what a knowledge graph for a paper looks like is the authors that are related to different concepts, but also universities that they're related to, but also concepts that those universities are related to. So it's really allowing you to build a sort of relationship link system that one can look at to see how things are related.
One thing I think is important to highlight is knowledge graphs are deterministic.
Yes.
Right? Meaning that there is a right answer to say what is the relationship
between
for sure. Asha and Jake. Asha is following Jake. Jake is following Asha.
Exactly. Either I wrote that paper or I did not.
Yeah.
Right? Either I'm related to that concept or I am not. Right? There's no. It's not like a generative approach where
or like a transformer model.
Exactly.
Model.
Yeah. Where there is some uncertainty. There's no uncertainty with a knowledge graph because it is post you actually extracting that information. Mm-hmm. So yeah, it's just a way of displaying things.
Yeah. So would you say like the core difference is like a language model or a transformer based architecture is non-deterministic, meaning that there's some statistical probability that the relationship between Asha and Jake is following.
Yes.
But then not every time you run that, you're not guaranteed to have the answer be Asha is following Jake.
Yeah, you're not guaranteed to get the right answer. It's also where and how it gets used, right? Mm-hmm. A knowledge graph really is a visual display of information that I already have. Mm-hmm. I just probably have it in a form that doesn't make sense. So I might have this huge file that has, all the users and their relationship to other users, but it doesn't make a lot of sense to me because I'm not a machine. Like I can't read a file with a bunch of lines. Yeah. So I put it into the knowledge graph, and now I can actually see a graph of this dot has a line connected to that dot, versus an LLM, for instance, would be doing the extraction for me. So I might give it the paper and ask it to make those extractions. So it's really where I use it in the process, and what I'm using it for also is completely different too. Okay. But yes, determinism is another thing.
Okay.
Yeah.
So you were basically taking language models and using them to generate these deterministic knowledge graph type relationships. Exactly. On scientific papers.
Exactly, yeah. I was using the language models to do the initial extraction of information. So again, what are the major concepts or methods from a paper? And then I would use the knowledge graph as just a visual display that would make it easier for the human to understand how things are connected and also how often they're connected, right? So maybe somebody's done work on ecology in relation to particle physics for some reason. Okay. That one guy did that one time. Mm-hmm. I don't really need to see that relationship's not as important to me as particle physics in relationship to like hardware sciences, which is going to have way more links. So what you also get to do is like add weights to relationships with a knowledge graph, so you can see what's actually important, how many times things are actually linked.
Okay, so you do this process for physics research.
Yeah.
What is kind of the findings of that, and where did that kind of lead you next?
Yeah. So why I ended up actually saying I'm just gonna like van down by the river and leave Fermi and work on this cool thing. It's because the LLMs at the time weren't ready. So, like I said, they did really well when it came to extracting basic topics from like the abstracts of papers, or abstract is just the introduction of a paper for those listening. Did really well at that. Did really well at helping me link information to feed to the knowledge graph. Where they really struggled at the time, though, was that domain awareness. And so what I mean by that is, if you read a paper on, I assume you're not an economist, right?
No.
Maybe not.
Not a formal economist, definitely.
Fair enough.
I'm like an armchair economist.
Unreal.
Yeah.
If we read like a paper on like Austrian economics right now, you and I, we probably wouldn't be able to tell you what the most important insights from that paper are, because we are not economists.
Yeah.
We don't know. Same thing with physics, right? If this model doesn't really have the context to say why something is important, then I can't expect it to actually give me the important concept from the paper. And so that was really the big problem. What I was looking for was trying to see, again, those forks in research to tell me, okay, what is the important iterative gain that we got from this paper based on this old thing?
Yeah.
And
what is the new areas of research that were opened up because of the findings of this other previous research?
Exactly. And if you don't have domain awareness, and I can't give you domain awareness, you can't do that. You also can't tell me what cool conclusions I could get from working on this paper in the future. So what I mean by that is, if I found a cool paper and it had some future questions that hadn't been answered yet, you can't really give me a pathway to get to those future questions, because again, you don't have any domain awareness.
Yeah.
And so what I wanted to work on was actually adding domain awareness to those models, which kind of, again, spurred me saying, I think I'm going to quit and do something cool.
Okay, so you quit this job at Fermilab and then went to go live in a van down by the river and basically work on this problem of adding domain awareness to language models.
Yes.
So that you could better generate knowledge graphs from scientific literature.
Yeah. So it really started with knowledge graphs. I didn't know anything about startups at the time. So my idea of building what I was building was not that I was going to build a startup or that it was going to be a platform. It was just going to be a cool thing I was going to throw up and lose some money on it. Maybe I would get a grant to help me host it, whatever. But what I really wanted to do from that was, okay, I've got this really cool prototype of a knowledge graph. There's a lot more information on what's called RAG coming out, so retrieval augmented generation, that essentially says that I can build my own library of information on physics and feed it to an LLM. There's now a method to do that. Cool. Somebody's kind of solved it, right? We've started to actually create methods for it.
And that's a way to kind of add some level of domain awareness.
Yeah. If I can say, here's some important information on physics at large that you should know when you're making decisions for my model, it makes much better decisions at the end of the day. So with seeing all this cool stuff, I said, well, it's like, screw the knowledge graph, right? We can go so much further with this. And so what I really got interested in was this idea of replication. So part of what I mentioned earlier about why I got interested in the quantitative epistemology with my advisor at the time was that we were trying to replicate papers, even for the galaxy classification thing that I mentioned. We were trying to replicate papers that seemed to have great conclusions, seemed to have solved the problem, and we could not. We couldn't because there was no data, bad data, or just straight up didn't work. And it didn't work so badly that it was probably like fabricated to some degree.
Let's talk a little bit about replication and how important replication is for science. So what is replication in a scientific research context?
Yeah, so I'll actually look a little larger than go down. There is this idea in research of validation, right? Research validation. Research validation is really 4 points. Claim verification, where you're just checking if basic claims are true in comparison to the literature, or they match the literary consensus.
So I, as a paper writer, will make this claim that says, all spiral galaxies are generated when black holes collide or something.
Yeah.
And that claim needs to be based in some underlying research.
Exactly. What does the rest of the literature say? Basically, as claim verification. If 9 of us say, well, no, that's not how spiral galaxies are created, then we have to throw your claim into question.
Yes.
And you could be right, but 9 against 1. So claim verification. The second is reproduction. So reproduction basically just says, let's say you have an algorithm in one of your papers. I can create some Python code to reproduce that algorithm. What replication is, and I'll just stop on this one as the third one because it's the most important to me, is can I take the work that you've done and make it work in the wild? Can I actually replicate your results on my end?
Yeah, so given the same data that you say you have and the
Yes.
same algorithm that you say you used,
Correct.
is my outcome the same as your
Yes.
outcome?
Can I literally replicate your results? And oftentimes you cannot. Replication is actually quite a rare event. It's hard. Doing high quality research is hard, but also there is a publish or perish mentality that sometimes inspires the creation of work that is probably error ridden. It's probably error prone with the statistics. It's probably error prone if there's any math involved. There's probably environmental specific things with your compute setup or your environment setup or your lab setup that I don't have that you didn't tell me about. There's all these things that aren't just people wanting to lie. It's error, a lot of it, getting in the way of us actually having replicable research. And so for me, especially when it came to a lot of computational work, I'm like, do you know how many hours I could have saved myself if I had a GPT to do that work for me? And so I didn't see anybody else really having that conversation at the time. And so I was like, hell yeah, I'm going to build it. This would be super cool for people to just have this portable tool to do that work.
And really quick, like touch on why it's so important that scientific research has this ability to be replicable and reproducible. Like what are the downsides if it's not?
The downsides are science really is, and I say this all the time now, the driver of the global modern economy. You probably would have a hard time naming a megacorp or a corporation that provides some good to your life right now that does not have R&D as a driver of the engine of what makes that company work. It just doesn't happen. But even more importantly, bad science means that lives are paused and lives are lost. So one example that I use all the time of bad science having the worst outcomes possible are some of the recent scandals and not so recent scandals with Alzheimer's work, where you have this handful of seminal papers that contain essentially just entirely fabricated data that we could have caught with not even particularly clever statistical methods back then, not even particularly clever image manipulation detectors back then, would have saved us 17 years of research, hundreds of millions of dollars, billions of dollars actually, if you tally it all up, and lives that are being racked by Alzheimer's every day. Not just the lives of the patients, but also the lives of their families.
Yeah.
And so that's an example of just the outsized impact that bad science has. It's literally the hands of science are on everything that we do.
So because, like, just to get a little more specific, because these papers were fabricated, the images of the results were actually edited to create a different claim within that paper.
Exactly. So the images of the results were duplications from other papers that had then been spliced and diced and fried, dilated to the side to say something that they weren't actually saying.
And so the impact of that then is you have this claim that is not true
at all.
And other people are then basing their new research off of this claim that is just fundamentally false.
Absolutely.
So it's a waste of time.
Yes. Not only some people, most of the field is basing their research off of 5 or 6 papers that are completely false. And it didn't just happen one time. It happened that one time 17, I think 18 now years ago. It also happened again with a separate lab in 2023 or 2022. Similar thing, right? Images completely fabricated. And not just we made a mistake. Images are fabricated, manipulated. We have the EXIF data. We have the metadata to say that they're manipulated. And yet still people say, okay, this is working. Let us put our dollars into this. And researchers are like any other occupation. They're mostly going to go where the dollars go when it comes to things that are being commercialized. And so what that says to me is, or what that should say to anybody is, it is a very important decision for you as a funder, you as a researcher, anyone involved with that, to make sure that if something makes grandiose claims, those claims better damn well be true before you put money behind it.
You better be able to replicate them.
Exactly. Before you put money behind it, hell, before you publish it, but especially before you put money behind it, make sure it's true. We don't have a system to even catch the basics right now. It's kind of the problem. Like I said, the one 17 years ago could have been caught with things that existed then that weren't even particularly clever. Like, it wasn't good fraud.
So traditionally, the way that the world has kind of solved this problem is the peer review process, right? So when you want to publish research, before you can publish it in a scientific journal, basically tell us what peer review is and kind of the role that it plays in science.
So peer review means that if I'm doing research, right? I'm a researcher. I did this really cool experiment. I want to tell everybody about it. I'm going to write a paper. I am going to try to share that paper, and the way that I'm going to share it is either through a journal, so journals publish research papers, or I'm going to go to a conference that's based around research or a workshop based around research. When I publish to any of these venues, what's going to happen is the editors at that venue are going to find a court of my peers, at least probably 2 or 3 of them that are in my same niche, to hopefully read over this paper over the course of, if you're lucky, maybe 2 months, sometimes over a year, not uncommon, but usually about 2 months to 6 or 7 months to read over my paper and make sure that it's good. Now, you would think, because I said 2 months to 7 months and sometimes over a year, that the review contents are usually worthwhile, but they are not. And that is not just my judgment, right? There is meta-science, right? So the science of science research that says that most researchers do not necessarily gain a lot from the review contents that they actually get back from peer review. Who actually ends up gaining, if there is any gain, is the peer reviewer, because they learn more about their field, not necessarily the reviewer. And that's great, but it's kind of like, okay, great. Another thing that's kind of wrong with that is they're not a machine. If there is a mathematical statistical error that proliferates through the paper and completely invalidates it, they're not going to catch it. They're not going to look at your data and code. They are not going to do image analysis with external tools. It's just not going to happen.
And why is that?
It's not nefarious. They don't have the time. Just like you're a researcher that's strapped for time, they are too. They're also not paid for this. They're not paid to do this work. Some editors get headhunting fees to find reviewers, but reviewers generally are not being paid to actually review papers.
They're just doing it kind of out of the goodness
of
their heart
altruism,
and the
for sure.
advancement of science in general.
Yeah, a lot of core science really moves on altruism. And although there is some benefit to that, and it does show sort of the integrity of the research community at large, let me be clear, it is not enough to be the core of how we are going about doing science.
Yeah, especially now that science is much more computationally based. You're now asking a researcher who's very busy doing their own research, et cetera, to take time out of their day to work for free to validate this.
Correct.
And you're somehow expecting them to now actually like take all the data and take the algorithms, et cetera, and like put in all this extra work on top of what is already extra work that they're not compensated for.
Exactly.
Yeah.
And there's a cacophony of tools that allege to do some of that work for them. None of them are very good. There's no standard, so it's the wild, wild west. On top of that, like I mentioned earlier briefly, you also have this sort of publish or perish mentality where not only up-and-coming researchers, but researchers that are tenured, that are fellows, that have been around the game for a long time, have this constantly looming thing in their ear where the existing bureaucracies are just saying, publish, publish, publish. The way that you're going to be great is how are you publishing, what are you publishing, how much are you publishing? Not necessarily taking into account outsized impact of what one could be publishing for their field.
And so that's like kind of the incentive structure that we have created around science.
Yeah.
Right? Universities get funding to pursue different forms of research.
Yes.
And in order for a researcher to be successful and grow in their career, they need to publish because that's how they then get the money to do additional research.
Exactly.
Right? And so if you're a university, you want this grant funding so that you can grow your business as a university, and that requires your scientists on staff essentially to do new novel research, get it published. Right?
So here's the thing: it encourages them to do more research. Where there's an issue is it likely does not encourage them to do novel research.
Yeah.
So another thing that I ran into, and that is very common for people to run into, I heard a lot of my older fellows in the research community or my colleagues complain about it all the time, is that when you're doing that grant shuffle, you're writing your proposal, ready to put your grant proposal in and whatnot, you pretty much probably know if you look at what other people are writing, what's going to get funded. And it's not necessarily going to be the thing that's novel. It's going to be the thing that matches an ongoing trend on how we're doing research at the time, or it's safe. And so not only are we encouraging people to produce more, we are encouraging them to produce more that's less disruptive. And so what we've essentially seen, again, this is another thing that's studied quite a bit in meta science, disruption indicators, is that disruption indicators in science, i.e. how novel or impactful the ideas we're actually studying are, have plummeted over time. We're actually going through a period of what's being called slowed canonical progress in the sciences at large.
Let's break that down. Slowed canonical progress.
Slowed canonical progress in the sciences at large, yes. So what that means on its face is that if you look across every major discipline, there has been, again, a plummeting in the amount of disruptive ideas that have actually happened over time, including artificial intelligence. I think that artificial intelligence gets away with a lot of this because we tend to go through cycles of focusing on different architectures. Right now, it's the LLM, VLM. Before the transformer, it was RL. Right? Before RL, it was how can we apply RNNs to stuff, so on and so forth. That'll probably continue, actually, post-LLMs. And so while that seems good, artificial intelligence is more than finding single architectures. It's such a huge field, and the other spaces in the field at large actually probably aren't moving as quickly as they could and are also going through this period of slowed canonical progress. Less than other fields. Physics has it bad.
But like as an example, it's probably really hard to do research on recursive neural networks, RNNs.
Sure.
Because kind of the canon right now is transformer architectures.
Exactly.
Right? And because that research isn't getting funded, any potentially disruptive outcomes of that research are just not happening.
Exactly. Yeah. You're lucky, right, if you're studying like RL, which is reinforcement learning. If you've, for context for the audience, seen some of those early YouTube videos of like machine learning models or deep learning models playing Mario Party. That's reinforcement learning. It does a bunch of stuff and it's rewarded for making the right decisions, so it learns how to do different tasks. You're lucky that that can kind of be, that is like a co-author when it comes to research, right? RL can be put on top of different architectures because it's just a way of going about doing something. Not necessarily an entire architecture itself. But yeah, you're right. Like if I wanted to study RNNs for some reason, if I wanted to study GNNs, graph neural networks, I got to find a way to throw LLMs in there to make it cool. Or just appear at conferences to get funded, but also just to appear at a conference. If I want to apply to NeurIPS right now, Neural Information Processing Conference, it's the biggest AI conference for research, period, happens in December. If I'm not publishing on LLMs or in relation to transformers or something that can even be tangentially related, I'm going to have less opportunities to get accepted to that or the workshops that they're putting on, right? It's just probably not going to happen.
And getting accepted to those things is how you as a researcher progress in your career.
Exactly.
Yeah,
so
thank you. I love Chuck. Breaking down kind of the incentive structures around science.
Yes. Yeah, there's a really thick layer of poor incentives in science at large, and we are bearing the brunt of that right now. It's like I said, we are going through an era of slowed canonical progress and likely still in the midst of what we've been calling for a long time a replicability crisis. So, yeah.
And right the replicability crisis basically just means a lot of this new research that's being published, you can't replicate it.
Yeah, you cannot replicate it. A better way to put it, it's probably not able to be replicated.
Yeah.
We can't even get as far as saying for sure that we can't replicate it because the research volume is not meeting, the research volume is outranking the tools that we have to even do research validation at the level that we need to do it.
So there's not enough peer reviewers to review all the papers that are trying to be published?
Not at all, no. And there need to be automated systems there to help people for sure. And there can be. We have the technology for it now.
Okay. And so this is, I mean, I guess like a perfect segue into Symby, right? So you go to a van down by the river, you start using...
I did get the van, by the way.
You start using GPT and like RAG techniques to start kind of creating this essentially like understanding of how different topics relate to each other. Like, I guess take us from there. Like, what was kind of the next step?
Yeah, for sure. So I had used to have a co-founder, my good friend at the time, Michael, who you know previously. was wanting to work on it with me. He had an idea that he wanted to implement way back in the day of like a blockchain style journal. But he wasn't an academic. So he knew nothing about how to implement journals.
He was just a cracked engineer.
Exactly. And he was like, I want to do something with it. And I said, boy, do I have an idea for you. And so we started working on it together. And what we saw is that, again, knowledge graphs are cool. Building a knowledge graph with more context than what's usually offered is cool, but the real goal here would be to build that technological infrastructure to essentially automate research validation. That didn't exist, and conversations about it at the time really didn't exist anywhere that we were, around.
So instead of just having someone peer review this paper, which there's all these human reasons why they might miss things, you could combine that with actually an automated system to do some of these checks.
Exactly, yeah. Completely streamline the process, but also make sure that you improve the efficacy of what's actually coming out of this. So, hey, even on the face, right, we're not just looking at the paper. We can also now look at your data and code and give you an overall quality metric for your experiment at large. And so what we really wanted to do was make something where we are not just looking at research as a static paper, but a dynamic project that's changing and has all these related assets. And so we started building it together. Michael was a little bit more knowledgeable about startups. And when I say knowledgeable, I mean he meant that they existed. He knew like Y Combinator was a thing and that like Silicon Valley was a thing. I knew nothing about it. And so then what we decided to do was take Symby from this abstract idea that we were going to build out loud and actually turn it into the platform to do that. And so for context, before I go forward, what Symby is at its core is automated research validation. And so you upload a paper, a patent, a grant proposal, any sort of research record you find in the wild to our platform, and we automate the validation process for you. We do auto replication, auto reproduction, claim verification, but also, even more importantly, we're a large library of research that you can essentially be comfortable with and know that we give you the native truth. What research actually exists, is that verifiable that you can use? We also build different tools for allowing you to search through your libraries of research a lot more easily. And so that's what Symby was and is, and that's what we decided that we wanted to build. Making it into a platform is going to be a little bit more difficult because researchers as a segment were actually, and I think still are, quite underserved. And so that's where I was really happy to have Michael by my side, somebody to kind of explore, okay, we know how to build the thing, but how do we actually build a platform that people want to use?
Yeah, how do we turn it into self-sustaining, profitable business so that we can do this?
Yes, and we had a long road. Yeah. Still have a long road.
For sure. That's the journey though, right?
Indeed. Yeah, for sure.
Cool. So that's kind of like the kind of initial like vision.
Yeah.
Take us from there, right? So you have this kind of like larger vision.
Yep.
You then start building the thing, right?
Indeed.
What did that process look like? Like, what does it take to build a system that can automatically replicate, validate, evaluate claims in research papers?
It's hard. So two things made it hard, or two things make it hard. It's still hard. I'm not even going to lie to you.
Yeah.
Our customers, I respect them very much so. And I know that what they're looking for when they think about platforms that they want to put their research through are, I know what's happening with my data. I can trust what you're doing with my data and with other people's work. And I have some transparency on how you're making decisions. And so for us, from day one, it wasn't going to work to just like plug Chat GPT or I think it was GPT-4 at the time, maybe 3.5, into the platform and say, do the thing. We had to use an architecture that was proprietary to us that we're constantly building out that gave transparency, that gave transparency analysis. So basically anything that we produce, we tell you why we've produced it. It's available to the user. Confidence scores, so you can see how we followed on the scale of confidence if we're producing something for you. But also we had to implement certain privacy features. So we don't train or do inference directly on your information. We basically create like a hash, or we look at the patterns of your stuff and work with that instead of looking directly at your data. And so that's what we were having to implement like day one if we knew we wanted to serve researchers, which made it such that even building a prototype for us wasn't just put the thing in the thing and then get the output. It was a lot harder. That's part one. Part two is that we actually found out the models, and we do use multiple models. We're LLMs, we use CNNs for computer vision. We use statistics and heuristics that just work if we don't need deep learning. But the part two is that the models, easy to figure them out, not particularly hard to build them once you know what you're building. It just takes a little bit more upstart time. What is really important, and what I'm really finding is more important than I thought even at the time, as I meet more people and think about how people are thinking about AI for science stuff, is the actual engineering architecture that exists around these models. And so we're not just serving you output from the models, we're having to build these really complex pipelines of like data engineering magistry, basically. And it's not easy.
So
like, it's not
kind of
easy
similar to your work at the Smithsonian. You've now got like this trillions of these different data points.
Indeed.
You need the architecture to be able to do that over and over again.
For sure.
Type things the right spot, et cetera.
Exactly.
Yeah.
Like even, so the data engineering, but even like the safety mechanisms around it. We're working with generative output. As you gave a great example earlier about how you can get this, you can, ping Claude over and over, and it might give you different answers on whether we're connected on the social media platform or not. That is the same case with us. Hallucinations, i.e. LLMs or transformers, sometimes making things up, right? Or giving answers that are completely incorrect. It does happen. But we can also experience prompt injection. There was a recent really high-profile news article where well, not us, but it was found that a huge segment of research papers had prompt injections in them to only give them positive reviews. So we're having to, now thankfully for us, that's not a problem. We look for that. But we have to build the system to look for that.
Yeah, you
it's
need
not particularly
some
easy.
sort of way to build those checks into the system.
Exactly.
Again, so that these researchers, your customers primarily,
Exactly.
feel confident using your system.
Yeah, exactly. So we really have to think very hard about the edge cases before other people know about the edge cases. We've been lucky to do that because this is our lifeline. This is what we want to do as a team, but it's not particularly easy. So yeah, that's the hard part for us. We can't just use off-the-shelf models. We can use some open source stuff and tweak it, which is fantastic, but we can't just again, throw GPT in there. And then also we have to be not just prescient, but ahead of the curve when it comes to a lot of the edge cases, constantly, because people are coming up with new things every day, trust me.
Like new ways basically to hack systems.
Oh yeah.
Yeah.
New jailbreaks, new actual jailbreaks on just regular engineering standards, right? Even when it comes to how we network and how we serve data, we're constantly having to be on top of it over there, but especially with relation to the models as well. There are constantly new and enterprising ways to jailbreak these models. I'm fine.
Criminals are very innovative in many ways.
For sure.
Right?
I like that about them. That they are, yes.
You gotta respect it.
Indeed, yes.
Begrudgingly.
I'm like, how are you a researcher and a criminal? I don't know, but I love that for you. So, but yeah.
Okay, so you've been on this journey for, how long have you been building Symby now? 3 years, 2 years?
Like 3 years.
3 years.
Yeah, 3 years. We've only really been a startup for some months over a year, maybe like a year and a half now. But yeah, the idea of Symby is at least 3 years old. Yeah.
Yeah. So you've been working on it for this long, year and a half. To help me understand kind of the progress thus far.
Oh my God, what a question.
Well, this is the fun one because you get to talk about all the cool stuff that you've built
Indeed.
and validated and put into the wild now to actually help solve this problem.
Yeah, indeed. The first 2 years of Symby, and this kind of shows you the importance of the fundamentals when it comes to building deep learning systems at large. LLMs are like any other architecture where the data does do a lot of the work, right? It's the data and the engineering that you build around these models does so much of the legwork. So for us, that first real 2 years of Symby was building this huge corpus of cross-disciplinary data. And we didn't even capture all the disciplines, right? We got what we could from open access sources of information online, and having a huge advisory council of people, I think we're up to 433 today, help us manually curate that data so that we have, I think, one of the biggest, if not the biggest, corpuses of manually curated research-related data. And so what I mean by that is we don't just have a bunch of papers. We have papers extracted down to very specific information, what's important about those papers, but we also have internal image data sets that lay out important types of images that you'll usually see in a paper. So for instance, there's a type of plot called a light curve in astrophysics or in physics at large. We know what a light curve should look like. We're able to build specific detector systems for if there's something weird about that particular light curve. And so imagine being able to do that, but basically for every type of sub-image in a bunch of disciplines. We can do that.
And when you talk about the manual curation piece, like why is that so important?
Well, that's important because although there's been a lot of progress with building synthetic data using LLMs actually, they still leave a lot to the imagination or a lot on the table when it comes to building synthetic data that actually requires, like, again, domain knowledge.
Yeah.
And so, great, you can build like synthetic human faces with a generative model, but building fake research papers, right, or building that look good, or building fake light curves that look good that you can actually learn from, it's not there. It's also really important to us that we are accurate if we're saying that something is an outlier.
Yeah.
And so for us, synthetic data doesn't really cut it, right? You can't, again, if you don't have the domain awareness, you can't make it. But even if you could, if we can use real information, it's always better.
So
it's
these
like the
400 plus cross-disciplinary researchers, PhDs, basically are like, I want to help you solve the replicability crisis.
Pretty
Let me
much.
help contribute to ultimately like the model that allows you to solve this problem.
Absolutely. And their best contribution has been with data. What we've also done that I'm really proud of, I need to finish this damn paper, is we did a large-scale replication study. Sometimes called a large-scale review study, same thing, where what we did was take a subsegment of them that work in physics, biology, math, stats, so just a couple disciplines, and we ran Symby against them as human reviewers and had human meta reviewers grade them. And so we were able to, in the wild, see if AI systems, not just Symby, but we also tried GPT-4 and I think Claude 4 at the time, against these human reviewers. We were also able to see the psychological impact of using AI in peer review on human reviewers. And what we found that was really interesting with this council of people was that using AI, not only was AI plus human the best reviewer, according to the meta reviewers, AI alone was not only competitive, but sometimes superseded humans, quite frequently superseded humans. But also, if you include AI in the review process, humans actually perform better.
Yeah.
So, which was interesting.
And this is not general AI, right? This is like your specific model that you've trained because of all this manual curation from all these PhDs.
Exactly. But let me give them their credit where credit is due. GPT-4 and Claude 4, they were behind humans, but the gap wasn't large.
Okay.
And so I don't actually think it'll be that much time, depending on kind of where these models go in the future, and if people want to build intentional architectures with them that they can use for their own use case for small things, where that gap will close. They weren't too far behind the curve. But what our paper shows was, again, not only are sort of, we call it symbiogenerative, so human plus AI reviews the best, AI can supersede humans if the architecture around it is intentional.
Yeah.
Which was a really, really big finding for us. But yeah, we had that advisory council that helped us with stuff like that. On the data set we spent 2 years on, they helped us do that and are just generally giving us feedback about their discipline at large. So if there's anybody listening that's interested in that, please contact. Yes. We are looking for as much discipline and diversity as we can. So right now we're hugely skewed towards physics, bio, physics, math, stats, bio, chem, in that order. That's generally because those are who I know, right? I know physicists that know physicists. I know mathematicians that know mathematicians. But we're looking for geologists. We're looking for entomologists. We have two. We're looking for econ folks. And what we're seeing right now is that the skew of our scientific advisory council, you can also see it in our success. When it comes
those
to
other domains.
Exactly. When it comes to how the model performs in those other domains, it actually does pretty well across disciplines. What we found is that you can transfer success in domain awareness from one discipline to another fairly easily. We still don't quite understand why, but we found that, for instance, when we were able to bolster the number of bio folk that we had on the board and we were able to do more manual curation there, we could directly see an improvement in performance in proprietary models. And so we're always looking for people to join in different disciplines for sure.
That makes sense.
Yeah.
So tell us a little bit about your customers. Like, what does kind of your customer base look like today?
For sure. So for us, we have pretty much always said that we wanted to start with the publishers. When you think about science at large, they make a lot of money. They make bank. They are underserved in that you usually don't see a lot of people selling to them, despite their need for tools and discontent with the tools that they do use. However, they are, compared to like a commercial R&D, a smaller segment, like by far, because there's not that many of them comparatively. And the really, really big dollars are skewed towards, top thousands of them. For us, though, that wasn't necessarily a negative place to start, because that's where all the research is generally going to end up.
Yeah.
If it's not going to a conference, if it's not being internally deployed secretly, it's going to go to a journal or a publisher of some sort. And so for us, it was a shoo-in. Not much competition. They have expressed a need, and they have the money to pay for it. And it looks good on us to penetrate these other markets that aren't as easy if we have the publishers on our side. And so that actually bear a lot of fruit for us, in that our earliest contracts, largest contracts, were publishers. We still have a huge publisher focus now. At this point, though, there is definitely a greater mix of commercial R&D. So when it comes to the publishers that we have, or customers that we have on board as contracts, but also as LOIs, it's not one is outdoing the other, or there's more than one than the other. It's a good mix of publishers, a good mix of, clinical research systems, a good mix of, your research institute here, your computer hardware company here, your such and such here. So we really do serve publishers and different facets of commercial R&D at the moment. Yeah. So, yeah.
Talk a little bit about also kind of one of the ideas that we talked about when we first met was, in order to gain the trust of scientists, like scientists that aren't on your board, that don't know all of the work that's gone into building this system, like building trust almost requires you to be trusted by the publishers, so that researchers will actually be willing to put their information through the system.
Absolutely, for sure. The publishers are really an important entry point for us. With that, building that trust. Another thing that I do for trust, if I am talking to an individual researcher or if I am talking to somebody commercial, I try to be a person of little words. Try it out.
Yeah.
Tell me what you think. Get back to me in 3 weeks.
Actions speak louder than words.
Exactly.
Yeah, let the results speak for themselves.
And so, although we do have an ornery market, or publishers are considered a little bit of an ornery market, it's actually quite simple in that you don't necessarily have to put on the salesman hat. You build something cool, build something useful, listen to them, give them what they want, and if they decide that they want to go forward, they will go forward. But as you said, getting our foot in the door, though, the publishers are really important for that. Is just hey, we're just the gold star standard thing that they use in the background. Get to know us. And if you like us enough, you'll probably want to use us for your own, on your own accord, on your own time.
So can you share a few of the publishers that you're currently working with?
Yes. So the one that I am super duper excited about is ACM, so Association of Computing Machinery. That's a big one for us. Big because not only because of the actual size of the company, but also because of the needs that are there. So it'll really allow us to get our feet dirty with saying, do we have the right workflow, or are we building the right workflows for working with not just one journal, but working with this huge giant that has different journals that are a part of them, that has different needs, etc. Another reason that I'm really excited to work with large publishers, or just publishers in general, but especially large publishers, is because, again, they are usually a part of networks that aren't just publishers, right? There are different entities that are looking at these publishers as central entities for not only the research that's being deployed, but how that research is being deployed, how that research is being evaluated, etc. It's also really cool to see a publisher like that taking research integrity seriously. I think more of these publishers are definitely willing to have the conversation and starting the conversation, but to see them be so early to it was really cool. So,
yeah, and ACM is, like, for people who don't know, it's kind of the leading machine learning research journal.
Yeah, they have a number of machine learning research journals, but it's just computing generally. So yeah, if you are into anything in relation to computing research, you've probably worked with in tandem, or been or are aware of at least an ACM journal or even event they do a lot of events and conferences as well. So super excited there.
Okay. And then how do individual researchers interface with your product, whether it's at a
Yeah.
journal or just individually?
Yeah, so in two ways. The first would be you work at insert publisher here, or you're submitting to a publisher and you use the Symby AI platform, or you work at commercial R&D company that wants to use or is using Symby AI internally to have a store of their internal research that they can search over, that they can validate, that they can use for experimental design. Or you can use Symby as just an individual researcher. So what we want to do and what we're hoping to do really soon this year is to just release the platform publicly as sort of a GitHub or Goodreads for research, where we are a platform that sits on top of research that already pretty much exists online or exists with our publisher customers. Another reason we like working with them, because we get all the cool secret stuff. Where you can go and not only look at papers, but look at verification methods that we've undertaken to say, hey, this paper, maybe you want to question this, or maybe look at this, but also just provide more valuable search tools for papers. One thing that we really hear from individual researchers that they want is just a better search for papers. And so there exist platforms where you can go and look at research at large and find papers, but there's not really a good platform that takes a refined approach to really giving you all of the literature that exists on that topic, but also helping you prioritize which literature you might want to use for your use case. And so we're really hoping to be that for the individual. So like I said, we have something coming for that, hopefully not too long from now. So
Okay.
yeah.
And then could theoretically, like if you're doing research,
Yeah.
could you use Symby to almost like refine that? Where Symby could tell you, hey, this claim that you make here, like you might want to beef up your evidence that supports that claim, because this paper like doesn't really quite give you the backing to make this claim.
Yeah.
So if you want to make this claim, you should probably beef it up with other substantial evidence to actually like improve the quality of research.
Yeah. That's a really common use case, right? People are very frequently referencing things that have been retracted, that are just outright wrong, and or are making a claim that you are not making in your paper when you are citing this thing.
Yeah.
And so that's a really common use case of saying, hey, maybe this foundation that you're using for your research you want to reconsider, or maybe you want to look at this piece of the literature that has some concerns about what you're working on. Yeah, that's very common.
Awesome. So what is kind of next in the pipeline? You mentioned once opening the platform up to like broader research base. Any other kind of inside info on like what's in the pipeline with Symby?
Yes, for sure. So there are two answers to this question. When I think about Symby, I've been sort of calling us in a foundational research lab in a trench coat. Okay. We are this platform company, right? We have this Symby platform that we're selling. But really, at the core of what we're doing, we want to, or the mission is, to create that technological engine that is going to push research validation into the stratosphere and give us something completely different from the substandard that we have right now when it comes to research validation. And so for us, when it comes to the Symby platform, we are thinking about even geographic expansion. So we spend a lot of time interfacing with the US because we're in the US, but we also think that the UK and the EU are at a really interesting point in trying to build out their technological independence. And so we want to do a lot more work there as well with the publishers there, but also the commercial R&D companies there, because we think that they're at a really interesting aspirational point that would be really interesting to help them build a foundation of AI validation tools, and they're asking for it. With that being said, back to the Frontier Lab in a trench coat, I also think that there's a really interesting research opportunity for Symby to bring the meta-science conversation to the US. And so what I mean by that is research validation, right? Making sure that research is verifiable and high quality is a form of meta-science, which is the science of science. I've been saying it this whole podcast. But essentially what that means is there's a growing group of researchers that are interested in studying how we optimize how we do science. It's a newish conversation. There's not really been this much of a concentrated effort or push from this amount of different institutions and people to study this, and there is still that missing technological standard to do so. We want to be that, but we also want to catalyzed the conversation in the US. We've been doing a lot of traveling to the UK and the EU because we see events happening there to start these conversations, and we see them growing, especially over the past 6 years. But we haven't quite seen that in the US, and we really think that it could start a chain event of almost a revival of how we are doing disruptive science in the US that we haven't seen for quite a while. And so, like I said, there are two different really big opportunities for Symby to be involved, and where I do see us becoming involved. On the platform side, geographic expansion, general expansion, becoming ubiquitous in the segments that we serve, but also on this research side where we have a really real opportunity to be that frontier research laboratory that is heading up this conversation in the United States.
Yeah, so in a similar way that like maybe DeepMind back in the day or OpenAI before it became commercial OpenAI was pushing forward research and discussion on AI, you guys can push forward discussion on like how are we doing science? How are we funding different types of research? Are we funding the right types of research?
Exactly.
It's very exciting.
Yeah, exactly. And I think that there's, even from like the general public, there's been, at the beginning of this year, right, with Doge, and just generally there is this idea of, can we build systems for efficiency? And, although one could argue that there are maybe problems with how that was gone about earlier this year, I do think that that's actually a really valid question. Not just for the everyday science that's happening at universities, but also what's happening at federal labs. What is happening when it comes to federal research funding, right? Do I think funding should be cut? No. But can we look at how we are funding things and make sure that we're not cutting out disruptive research and making sure that we are funding the things that are of a higher caliber? Yes, there's absolutely a lot of room for discussion there that just hasn't been had yet.
Going back to where we started this conversation, research engineering, right? Can you actually engineer the process of doing research to optimize it, make it more efficient, effective?
Exactly. Well, research engineers for the win. They are the future.
That's awesome. Well, now I'd like to move into kind of like a rapid fire section.
Okay.
Open to it. So
Okay,
I'll
let's
just
do
ask
it.
you questions and you kind of give me your answer.
Okay.
So first, what is like a book, podcast, like piece of content that has given you a framework that just influences the way that you think or live your life?
Gotcha. Okay. Two. I promise I'll be rapid fire. The first is Use of Human Beings by Norbert Weiner. It's a foundational book in the field of cybernetics, which informed the field of artificial intelligence. But essentially what it says is that humans and machines will probably do best if we build machines with the idea of like a human symbiosis. The idea of Symby kind of comes from there. And the second is how to do things. If anybody else struggles with being productive in the way that they would want to be, it essentially gives you a modified Pomodoro technique that is very helpful. Please use it. I will shill that book as often as I can.
This doesn't have to be too rapid. Tell me about modified Pomodoro technique.
Oh, yes. So How to Do Things by David Kane uses a Pomodoro technique that is modified to be more helpful for people with ADHD. I don't have ADHD, but what I find is that the Pomodoro technique is the use of specified time blocks to get work done. So usually you set a timer for 25 minutes, you work that 25 minutes, you take a 5-minute break, you do it again 3 times in a row, and then you take a longer break. What How to Do Things does in 50 pages is lay out a modified version of that technique that, again, is more aimed at people for whom Pomodoro technique doesn't work, but also may have executive function problems, or maybe doing work where it seems like the hard part is not the actual doing, but the prioritization of what you need to do.
Yeah.
So it takes a systems thinking approach to how to actually lay out the prioritization of tasks to get them done. And it's not as intuitive as people think it is. So again, I'm constantly shilling that book. But if you want a tangible how to get better book, read it, please. It changed my life.
Especially for like knowledge workers where like, a lot of the job is just prioritization.
Exactly.
Like, there's always more things to do, but how do you focus on the actual most important thing?
Yes.
I can see that being
and like efficiency is at the heart of the book. I guess it's 50 pages, and that sounds incredibly small, but it gets across every point that it needs to so incredibly efficiently that it makes its point on its face about what it's trying to get you to do. So yeah, it's really good.
Okay, next question.
Okay.
You see my Jake from State Farm mug. I love this, right?
Indeed.
If you could put a few words or a phrase or just an idea on the Ashia Lewis-Livaudais mug, what would those words or phrase be?
Go outside.
That's great.
No, seriously. So one thing that I've been learning too, task prioritization, and what I mean by that is when I'm prioritizing my tasks now, you do startup stuff, you think that everything is an on fire, critical thing.
Yeah.
I'm learning that for me, the number one task, if it's something on my list that falls into this category, is like go talk to somebody. Me just talking to people, whether it's I do a podcast with one of my favorite brains in the world, or I'm just talking to somebody that's at a startup event or a dev dinner, or go to Jake's Dev Dinners, or I go to a conference. The amount of connections that I make from just talking to people is incredible. The amount of new things that I learn about where I can take Symby, where I can take myself as a founder is incredible. So if I can prioritize talking to somebody, that needs to be task number one all the time. So go outside literally should be on the book.
Nice. No, that's really good.
Yeah.
That's a good one. Go outside. I love that. What is your favorite language model, just for personal use?
Oh, my favorite language model for personal use is, oh man, probably O3 or Quinn 3.
Okay.
Yeah. So I try to go open source. So I use Quinn 3 via OpenRouter, which OpenRouter is for context for anyone, a platform that allows you to switch models, and they do their own little internal systems prompting that makes it cheaper than usually if you were using it via a platform or hosting something yourself. So, yes.
Yeah. And then last, tell me about something difficult that you had to go through that ultimately ended up making you a better founder or researcher. Could be throughout your life.
Yeah, that's a good question. Well, in relation to the startup, you know this, but I lost my co-founder, essentially. They are alive. Maybe, allegedly. No, they're alive, but essentially my co-founder just decided that it wasn't a fit for them anymore. And one thing that's been really hard is being open to adaptation that requires the loss of something, or it feels like the loss of something in relation to being a founder. Being a founder, I think, is the best job in the world. I quite enjoy it. It's perfect for me. But losing, again, this person that I started the company with that allowed me to even feel comfortable to take the leap to do this was super duper hard, especially at such an important point where we were getting these larger enterprise contracts, where we were still in the thick of it when it came to engineering was particularly difficult. But it was also a sort of nut up or shut up moment where the next day I'm having to talk to my team, talk them through it, and just move on. I have people's livelihood in my hands. I have a team that was willing to support me and wanted to support me and cared about the mission. And so seeing them be so gung-ho about, that sucks, but what's next? What are we doing today? Really helped me through it. So I think having that experience again was very difficult, especially the mode or method with which it happened. But I'm actually kind of glad that it happened. One, because I do think that it wasn't a fit. It was a forced fit. But two, because it also showed me that, again, I have a team that's phenomenal and ready to go at all points, but also it didn't stop anything. So these things may seem catastrophic at the time, but the next day was the next day.
Yeah, what doesn't kill you makes you stronger.
Period.
Awesome. Well, Ashia, this has been, as always, a fascinating conversation. You're just one of my favorite people to talk to, whether it's about quantitative epistemology or reindeer farms or the really, really cool stuff you're building with Symby.
For sure.
For anyone that wants to get involved, follow you, etc., what are the best ways for them to do that?
Yes. So 2 ways. If you want to get involved, you can follow Symby AI, Symby AI on LinkedIn. Better than saying my name, Ashia Lewis-Livaudais, say that 5 times fast.
Spell that 5 times fast.
Honestly, I struggle myself. If you follow Symby AI, I'll definitely be linked either in a repost or in the people, so you can connect with me on there as well, but that's probably the best way. Yeah.
Cool. And we'll put all your info in the show notes.
Nice. Fantastic. I don't have to spell it.
Right on.
Awesome.
Ashia, thank you so much. This was awesome.
Awesome. Cool.
Great.
Thank you, sir.
Absolutely.